Hello everyone. The topic for this lecture is cross-site scripting, or in short, XSS. This is a very important topic because cross-site scripting is one of the most prevalent vulnerabilities in web applications, but at the same time is also one of the most underestimated vulnerabilities regarding the impact that it may cause. So what is cross-site scripting? The name of this vulnerability is not telling much, therefore let's just go directly to an example so that we can see what is the essence of it. So here is a classical example of an XSS vulnerability. Let's say we have a website with a search form where users can enter a keyword, and after submitting the form, the website shows the result for this keyword. As you see, in this use case, the website takes the user input submitted here and returns it back to the user here in the returned HTML code. And this is the point where the website potentially can introduce a cross-site scripting vulnerability. Because if the website just blindly takes whatever input is submitted here and without any processing puts this user input inside the returned HTML, then we can use this input parameter to inject arbitrary HTML code in the generated web page, which will result in a cross-site scripting vulnerability. In this case, we can very easily test whether this web page is vulnerable to XSS. For instance, we can use the HTML bold tags around our keyword, and we see that indeed our HTML tags are part of the returned HTML because our keyword now is rendered in boldface. So this pretty much tells us that this website is vulnerable to HTML injection or XSS. Note that we don't have to limit ourselves to HTML bold tags here. We can inject any HTML code, including JavaScript. For example, here we can submit a JavaScript code which will be executed by the web page and will result in an alert window containing the value 1, which we specified here. Now, this is definitely not the functionality that we wanted to provide to the user. And the reason for this is because we did not properly escape potential HTML code that is inside the user's input. If you look at the web application code that generated the web page, we can see that it takes the value from the get parameter q and puts it into the HTML code that will be returned by the server. And this is the generated HTML response that is received by the browser. Now, we do know that this part, these script tags, is actually part of the user's input that should have been just displayed, but the browser doesn't know it. It considers the entire response as a valid HTML code and renders it fully, executing the HTML code supplied by the user. Now, how should we fix this HTML code to actually display these script tags instead of interpreting them as HTML and executing? The answer is that we must replace all HTML special characters in this value with their respective HTML entities. The HTML special characters in this case are left and right angle brackets that are used to start and end HTML tags. So this is how a correctly generated HTML response should look. As you see, the angle brackets have been replaced with their HTML entities. And this is how it would look when rendered by a browser. As you see, our script tags are now displayed as text instead of being interpreted by the browser as HTML code. Here in PHP, we can call a special function to convert HTML special characters in this variable to HTML entities and thereby avoid introducing a vulnerability. We will talk more about how to avoid XSS in later slides, but before that, let's get back to our vulnerable web application and discuss how could we exploit this vulnerability. First of all, XSS is a client-side vulnerability, meaning that we cannot use it to compromise the server. What we can do, however, is we can compromise the client, more specifically, the victim's browser session with the vulnerable website. What it does is that it essentially enables arbitrary HTML code injection. And actually, HTML code injection is a better name for this vulnerability as it better conveys what this vulnerability is about. By injecting arbitrary HTML code, or more specifically a malicious JavaScript code, an attacker can get full control over the website, change how the website looks and behaves, and perform requests inside the website on behalf of the victim. Now, the limitation here is that the attacker's code will run only while the window tab is opened. In practice, however, if the attack is well prepared and does not require any user interaction, then the attack can achieve its goal in a matter of seconds before the victim gets bored and closes the window. We will talk more about the possible attack scenarios in a couple of slides, but at this point you may ask, how is this an attack if the victim is supposed to manually paste the attack code here to attack themselves? Indeed, for the attack to make sense, we need to somehow make this victim's browser to automatically submit this request without user interaction. So the exploitation here will be similar to cross-site request forgery. We will need to trick the victim to click on a link that contains the attack payload. So this here is the so-called reflected XSS attack, because the malicious input received in the HTTP request is reflected in the response back to the user's browser. Let's discuss more the exploitation of a reflected XSS vulnerability. So here we have an attacker who somehow tricks the victim's browser to make a request with an XSS payload to the vulnerable server, and as a result, the server reflects the XSS payload back to the victim's browser. So here, the victim must be tricked to perform a cross-origin request that contains the attack payload. In case of a GET-based XSS, this would mean opening a link with the attack payload, meaning that the attacker would have to send the link over email or paste it in a chat and make sure that the victim clicks on it. Here, a URL shortening service could be used to hide the attack payload from the link. In case of a post-based XSS, the HTML form auto-submission can be used, so the attacker would have to set up a website that, when opened by the victim, would automatically submit the post request to the vulnerable website. Note that the fetch API cannot be used here, as the response returned would not be rendered by the victim's browser. So, in contrast to the cross-site request forgery, here it is not enough to just make the request. We have to make sure that the response is rendered by the victim's browser, as only the rendering of the attack payload will cause its execution. So here it is hard to execute the attack in the background, as the victim will end up in the vulnerable website. A stealthy attack could be performed by using a hidden iframe, but this works only if the framing is allowed, meaning that the vulnerable website is not using the content security policy headers to prevent other websites from including it into an iframe. The framing would also enable a longer attack persistence, as the malicious code would run as long as the victim has the attacker's website open. So here the attacker could present some interesting content in order to keep the victim on the attacker's website for as long as it is necessary. Now, the biggest limitation of these reflected XSS attacks is that cross-origin requests may be restricted by the vulnerable website. For instance, the website may use the same site cookies or have other CSRF protection measures in place. This, however, would usually apply only to post-based requests. Therefore, exploiting GET-based reflected XSS might be more feasible. Another type of vulnerability is a stored XSS vulnerability. Compared to reflected XSS, stored XSS works a bit differently. First, an attacker makes a request with an XSS payload to the vulnerable website. The website stores it somewhere, usually in a database, and then when a victim's browser visits the website, the stored XSS payload is returned to the victim's browser. Think about an XSS payload in comment and feedback forms. For instance, in the scenario of public bulletin boards, where an attacker posts a payload in a comment field, and everyone who opens the comment page has the payload executed in their browsers. Users' profile information is also a very popular place in a social networking type of websites. An attacker can add a payload into their profile information, and anyone who opens a page that shows the attacker's profile information would have the payload executed. Then HTTP request headers can also be a field that may carry a stored XSS payload. For instance, inside the referrer and user agent headers. Admin panels are especially susceptible to this attack vector, as these type of headers are frequently extracted from audit logs and displayed to website administrators. So, compared to reflected XSS, stored XSS is more powerful because when injecting the XSS payload, the attacker is not limited by the forged cross-origin request that the victim's browser is capable of making when executing a reflected XSS attack. In a reflected XSS attack, an attacker cannot force the victim's browser to make a request using some specific header values, while in a stored XSS attack, the attacker has full control over the malicious request, and therefore any field of the request may contain attack payload and lead to XSS if that field is displayed to a user without proper encoding. So here the attacker is not affected by the cross-origin request restrictions. Also, this attack may not require social engineering for tricking a victim to click on the link, of course assuming that the victim themselves finds a way to the affected page in the website. Actually, this attack does not have to be targeted. So potentially there could be multiple targets, as anyone who visits the affected web page would get the XSS payload executed. Self-XSS is a vulnerability related to stored XSS, but here the limitation is that the stored payload is returned only to the attacker themselves. Usually, this vulnerability cannot be exploited, but it may become exploitable if the website has other vulnerabilities. For example, a login CSRF vulnerability, meaning that the attacker can force a victim to authenticate into the attacker's account on the vulnerable website. But alright, so these are the two most common types of XSS vulnerabilities. But let's discuss now how to exploit these vulnerabilities. First, let's talk about how to execute JavaScript code. From an attacker's perspective, it is very important to inject and execute JavaScript, because without the ability to execute JavaScript, it is much harder to achieve anything meaningful from XSS. Let's take a look at the possible locations where JavaScript code can reside inside an HTML document. Basically, there are 4 locations where we can put JavaScript code. The first one is placing JavaScript between script tags somewhere in the body of the HTML document. This is called inline JavaScript, and the code here will be executed immediately after it is processed. Then the JavaScript code can be placed in a separate file specified in the script tag's source attribute. The file name can be a relative URL pointing to a file on the same website, or it can be an absolute URL pointing to a script on some other website. Here it is important to point out that JavaScript runs in the origin that loads it and not the origin it was loaded from. This means that the result will be the same as if we placed the contents of this file directly in the inline script of our website. So from the security perspective, it is very dangerous to include scripts from other websites, as then these websites can execute an XSS attack against our website by placing malicious code in these scripts. We should do this only if we trust the owners of these websites. But even then, that website can get hacked, and the result will be that the attacker will be able to attack our website as well. So when possible, we should better place all scripts on our own website. Now, if we do have to execute scripts from other websites, we should use this integrity attribute where we can specify the hash value of the expected file. This way, if the server gets compromised and the contents of the file get changed, the browser will refuse to load the modified version as the hash of the file will change. Now, this is a nice feature, but it will require a coarse authorization when loading scripts from cross-origin websites. This is because without coarse authorization, this feature could be abused in access leaks, enabling malicious websites to check whether the response returned by cross-origin website matches a specific content. Therefore, we can use this Subresource Integrity feature only if it is supported by the cross-origin website. Then JavaScript code can be placed in event handlers such as onClick, onLoad, onError, and others. Here you can see it placed inside the image tags onError event handler. In this case, this JavaScript code will be executed when the browser will fail to fetch the image specified in this invalid URL. So the point is that the code specified in event handlers will fire only once that event is triggered. Some of the events, such as onClick, would actually require the user clicking somewhere, which might be a limitation in an XSS attack. Lastly, and rather unexpectedly, JavaScript code can also be placed in JavaScript and data URLs. Here are some examples of how JavaScript execution can be achieved. But note that this works only for some attributes that accept URLs, and there are some limitations. For example, a data URL in the source attribute of an iframe will execute in the null origin, as we discussed in a previous lecture. Alright, so these are the methods how we can execute JavaScript inside an HTML document. But the question is, what can an attacker achieve by injecting and executing arbitrary JavaScript code in a vulnerable website? Well, that depends on the attacker's JavaScript skills and imagination, but the short answer is that the attacker can do a lot. Stealing session cookies via XSS is one of the primary attacks an attacker would like to perform. Because if an attacker gets access to the secret value contained inside the authentication cookie, the attacker can load the cookie inside the browser and browse the user's account on the vulnerable website with the same experience as the legitimate user. This attack is also known as session hijacking. So here's how it could be done. First, a user has to authenticate to the vulnerable website, and as a response, the server will set a session cookie. So the goal of the attacker is to steal this cookie. Let's assume that the attacker has found a reflected XSS vulnerability in the website, and the attacker now crafts an attack payload which should submit the user's cookie to attacker.com. So what this script does is that it creates an image object in memory and sets the source attribute to this path. The path is constructed by appending to attacker.com the value contained in the document.cookie object. At this point, the browser will try to download this image, which will effectively request this URL from the attacker's controlled website, thereby leaking the value of the cookie to the attacker. Alternatively, the payload could simply redirect the user's browser to this URL. But this is a more stealthy attack, as this request is made in the background without the user's browser leaving the vulnerable website. Anyhow, the attack payload then is delivered to the user, and the user clicks on the exploit URL, and the user browser makes a request to the attacker's server with the user's cookies being embedded in the request URL. The attacker looks at the server logs and sees the cookie value in the path of the request. The attacker loads the cookie into a browser, refreshes the web page, and is logged into the website as the user, which is pretty bad for the user. Now, what could be the potential defense measures against such session hijacking? Well, of course, avoiding cross-site scripting vulnerabilities in a website, but actually avoiding XSS may be much harder in practice than it sounds. So one potential measure could be binding the session to the IP address and the browser's user agent. So in case the IP address or the browser version of a logged-in user changes, then the website simply ignores the received session cookie. Now, binding IP address to the authenticated session is actually quite problematic in practice, because today there are legitimate reasons why the IP address of a logged-in user may suddenly change. We don't want legitimate users to be logged out in such a case. Even more problematic is binding it to the user agent, because it is trivial for the attacker to find out the victim's user agent and set the same user agent in the attacker's browser. Actually, this request here will leak the user agent of the victim. Therefore, this is a very easy countermeasure for an attacker to bypass. HttpOnly cookies, however, is a very efficient measure against this type of cookie stealing attack. Therefore, let's take a closer look at the HttpOnly cookies. The HttpOnly attribute of the cookies forbids JavaScript from accessing the cookie. So if you set a cookie using the HttpOnly attribute, then it will not show up in the document.cookie object available in JavaScript, and therefore such a cookie cannot be stolen in an XSS attack. It is also not possible to set HttpOnly cookies using JavaScript. HttpOnly cookies can be set only using the setCookie response header. Therefore, as the best security practice, the HttpOnly attribute must be set for authentication cookies. There is really no good reason why JavaScript should be able to read these cookies. There might be some other cookies storing some user preferences. Now, making these available in JavaScript might be useful, but it is definitely not necessary for authentication cookies. Although what should be noted is that JavaScript can delete and override HTTP cookies. Actually, this cannot be done directly, but by executing the cookie Jar Overflow attack. The effect is that browsers store only a few hundreds of cookies per website, When more cookies are written, older cookies are removed. So by creating a lot of new cookies, we can push out older cookies, including HTTP-only cookies. Here you can see the attack code, which is quite simple. So this JavaScript code will create 700 cookies, and then this loop will delete the created cookies, effectively clearing all cookies for the website. Once HTTP-only cookies have been pushed out, we can create a non-HTTP-only cookie with the same name and scope, effectively overwriting the HTTP-only cookie. How can the attacker benefit from cookie overwriting attack? We have already discussed before. Note that cookie jars are isolated by origins. This means that other subdomains and insecure HTTP sites cannot use this attack to push out secure cookies from the user's browser. This cookie jar overflow attack would not be possible if browsers had separate storage limits for HTTP and non-HTTP cookies, but for some reason such separation has not been implemented, and therefore HTTP-only cookie overwriting from JavaScript is still possible. Let's take a quick look at some other XSS exploitation scenarios and their potential impact. Stealing autofilled passwords is a very powerful exploitation scenario. You may have noticed that browsers offer to save enter passwords, and the next time you visit a website, the browser will autofill the username and password fields. Now, guess what? A malicious JavaScript can read these autofilled values and send them to the attacker. Therefore, with an XSS attack, an attacker can simply add a password field somewhere in the body of the page, wait for the browser to autofill it, read out the values, and send them to the attacker's server. Depending on the browser used, the attacker might actually have to first trick the user into clicking anywhere on the page, but that should not be too hard to accomplish. In a way, this is a more powerful attack than the session cookie theft because now the attacker has the victim's username and password and can log into the victim's account whenever needed. Of course, assuming no two-factor authentication is required by the website. If stealing autofilled passwords does not work, the attacker can try stealing the victim's password by asking the re-entering of the password. For example, a pop-up can be shown that your session has timed out, and to continue browsing the site, please re-enter your username and password. And of course, when the username and password is entered, then they would be submitted to the attacker's server. Since this pop-up would be shown on the legitimate website, the user may feel safe entering the password. Then a similar social engineering trick could be used to fish out pretty much any other information from the user. So the only limit here is the imagination of a social engineer. Sending the contents of the page DOM to the attacker may also be useful, as this way the attacker can get to see what the user sees when visiting the vulnerable website. And this of course may contain quite sensitive information. Even more, the attacker can perform actions on behalf of the logged in user as if the user themselves would have clicked through the website. This can be used to change the account settings of the user, perform transactions, and so on. What we have to realize here is that XSS can be used to bypass all CSR protection measures. Since the attacker can use XSS to perform same origin requests and read back the responses, none of the standard CSRF protection measures will block such requests. So in essence, an XSS attack can give the attacker the same capabilities and user experience as if the attacker was sitting in front of the victim's computer and browsing the vulnerable website using the victim's browser. Defacement of the website and spreading disinformation is also an option. So this is probably the shortest defacement payload the attacker can use. It will replace the contents of the HTML body with a single line stating that the server has been hacked and all customer data stolen, which is not true when considering the nature of an XSS attack. Fake press releases can also appear to be published on a website, and anyone who clicks on the payload link and reads the information will consider it credible because it is displayed on the legitimate website. Performing the cookie bomb attack is an interesting one. Here the idea is to set a very big cookie via JavaScript. This will cause a denial of service condition when the user's browser will make future requests to the website. The reason is because web servers enforce a limit on the size of HTTP request headers. For most modern web servers, this limit is 8 kilobytes. So when a server receives a cookie header that is larger than 8 kilobytes, this server will return an error. Here's how it looks. Let's assume that we can execute arbitrary JavaScript code in this website. We can set 3 dummy cookies, each 4 kilobytes in size, and when the user browser will try to send any request to the server will return an error without the request even reaching the web application. So all future requests made to the website will be rejected until the user manually clears the website's cookies. The error message returned by the Nginx server indicates that the issue might be related to the size of cookies, but other web servers may return a more generic bad request error message, making the user assume that there is simply something wrong with the server. Pretty bad, right? Note that by manipulating with the path attribute, the attacker can block access to only specific sections of the website, which might be useful in some more advanced attacks. Now, what is even worse is that such cookie bomb attacks can be performed by any origin belonging to the same site, including the insecure HTTP origins. This works because a malicious subdomain can set the cookie's domain parameter to the root domain, which will include the cookie also in requests to all subdomains. Unfortunately, there is no opt-out mechanism for an origin to indicate that it does not want to receive cookies set by other domains of the same root domain. So you see, this is another example which shows the weakness of the same site policy, which is used for scoping HTTP cookies. Here it is also useful to mention that a website can become exposed to the cookie bomb attack also if it places a user-supplied input into cookies without enforcing proper size limits. For example, consider a website which puts the refer value into the cookie. An attacker can force a user's browser to make a cross-site request with a very long refer value, which will lead to a denial of service condition for the user. Therefore, a website should be very careful on what it places inside a cookie. Anyhow, so these are perhaps the most interesting XSS exploitation scenarios to mention. The takeaway here is that the impact of XSS can be quite severe, even though it is a client-side vulnerability that cannot be used to compromise the server. Let's move on to the topic of preventing XSS vulnerabilities. And there are a couple of things that we can do. The first thing is validation. We can validate all user input. We can check format and type. If we are expecting an integer, we should reject values that contain other characters than digits. If a value should contain an email address, we can apply a regular expression to check that the input contains a valid email address, and so on. Then we can validate the length of the input by specifying some reasonable limits. This is usually overlooked, but as you may have seen, sometimes limiting the length of the input field may make the exploitation of an XSS flaw very complicated, if not even impossible. Validation against a wide list of possible good values that the input may contain is also a very good solution, but it works only if we have a limited set of possible values that the user's input may contain. Of course, this will not work for free text input fields. The next approach is sanitization, where we can try removing bad characters and dangerous keywords from the user input. However, in practice, it is very tricky to achieve XSS protection through sanitization alone, and the side effect of sanitization is that we have a risk of losing functionality. For example, there might be a legitimate reason for a user to submit data that contains some special characters. If we filter them out, we lose a part of potentially legitimate information in the user's input. Encoding is the last and the most effective method to prevent XSS vulnerabilities. However, what makes it a bit complicated is that there are different encoding rules for different contexts. Therefore, we have to correctly understand in which context we are inserting untrusted user input and apply the corresponding encoding mechanism. So let's take a look at the most common encoding context that we will have to face when developing web applications. Encoding for the HTML context is the most basic and the most frequent encoding method that we have to use to prevent XSS. The HTML context here refers to inserting untrusted data between two basic HTML tags like a div. To encode this untrusted data here, we have to replace these 5 HTML special characters with these character sequences called HTML entities. Here's an example in PHP. So in PHP, we can use HTML special cars function with this parameter. Here you can see the output of this code. As you see, our attack payload here has been properly encoded and made HTML safe. Also, in practice, we may want to define a shortcut function to perform this encoding in many different places over our codebase. Now, this HTML entity encoding can also be used to encode safe HTML attribute values, such as the value attribute in the input tag and alt attribute in the image tag. So the HTML attribute values is another important HTML context where we may need to insert untrusted user input. But this can be done safely only for a limited set of HTML attributes that are considered safe. Here is the complete list of HTML attributes in whose values we can insert untrusted user input and make them XSS safe by applying the HTML entity encoding. In other HTML attribute values, we must not insert arbitrary user input. Others have to be strictly validated against the set of acceptable safe values. And another super important point to mention is that all attribute values must be quoted. So here must be quotes around the attribute value, as otherwise it is possible to trivially break out of this context by using, for example, the space character inside the untrusted data. It is also important to pass this end quotes parameter here, as otherwise the single quotes will not be encoded, and this will enable XSS in case single quotes are used here to prevent the user input from breaking out from the attribute values context. Let's look at the encoding for URL context. The URL context where we can use encoding is when we are inserting untrusted data into HTML URL parameter values. For instance, here where we have an href with hard-coded URL where the untrusted user input may only be part of the URL query parameter values. To prevent XSS in this context, we apply encoding where all non-alphanumeric characters, with the exception of few, are replaced with a percent sign followed by 2 hex digits. Here's an example in PHP. So here we would use the raw URL encode function on the untrusted user input. And this is how the output would look. As you see, our malicious exploit payload here has been URL encoded and neutralized. Instead of raw URL encode here, we could have also used HTML special cars. That will also neutralize attack payload, but here we have to use raw URL encode as we want to not just prevent XSS, but also to make the user input correctly decodable by the server when it receives this value in the query parameter. What should be stressed is that this encoding must not be applied for the entire untrusted value inserted into source or ref attributes. If we applied the URL encoding on the entire URL and not just the parameter values, then it would mess up the URL and it would not be any more a valid URL. There are also security considerations because we might not want to give the attacker control over the entire URL that goes into these attributes. So in a case where we have to insert untrusted user input in the entire URL, no encoding will help us. In such a case, we have to perform strict validation against allowed schemes, hostnames, and other URL components. Note that we must forbid the JavaScript and data URLs as they can be used to execute JavaScript. So that's it about the encoding for the URL context. Let's look at the encoding for the JavaScript context. The JavaScript context refers to a situation where we are inserting untrusted data in JavaScript variables. So the only safe location for placing variables in JavaScript is inside a quoted data value. All other contexts are unsafe and we should not place variable data into them. The data that we place here must be encoded by replacing these characters with these character sequences. Here's an example in PHP. So in PHP, we can use the JSON encode function with these parameters. It will perform this encoding. Here you can see the output of this code. As you see, our attack payload here has been properly encoded and made JavaScript safe. Also note that for security reasons, JSON encode will return the result in double quotes as you see here. So these double quotes here are part of the JSON encode output. Therefore, we did not put quotes around this code here. Note that there is still possible potential XSS downstream. For example, this will happen if we take this untrusted data and later insert it insecurely in the document object model, as you can see here using write or inner HTML. The problem is that this variable can contain HTML tags. By using JSON encode here, we made sure that we do not introduce XSS vector here in this line where the JavaScript variable is defined. After our browser processes this line, the variable x will actually contain the decoded and unsafe version of the string. Therefore, we have to be careful how we handle it downstream in our JavaScript code. The safe way to populate the DOM with untrusted data is to use the assignment property text content as you see here. And the last note to mention is that this practice of putting variable data inside inline JavaScript is a bad design pattern that should be avoided. It is actually possible to redesign our website and get rid of the need to encode anything for the JavaScript context. The workaround here is to put this untrusted user data in a hidden HTML element using the standard HTML context encoding, and then read the value with JavaScript using the getElementBy methods. Well, alright, so these were the 3 most common contexts where we would have to place user data when developing web applications. Let's look at some forbidden contexts which should not be used. Never put variable user input in these locations. Directly in a script. The only safe location for placing user input in JavaScript is inside a quoted data value, as we discussed on the previous slide. Don't put user input inside an HTML comment, in an attribute name, in a tag name, directly into CSS style tags. The problem is that if we put arbitrary user input anywhere here, no encoding will help, because there are so many unexpected ways how to break out from these contexts. Usually in web application development, there should be no need for us to put data in these contexts. However, if there is a strong need for that, then the only safe solution here is validation against a whitelist of known safe values, which may or may not be a solution depending on the use case. To summarize, most of the XSS vulnerabilities can be prevented by not placing data in forbidden contexts and using the appropriate encoding mechanism when placing data in the allowed contexts. However, there might be a need to apply HTML sanitization if we want to allow certain HTML tags but want to prevent script execution. This would be the case when we want users to style text, but we don't want them to insert any active elements such as JavaScript. To accomplish this, we can use the excellent DOMPurify JavaScript library. We can pass to it dirty, potentially malicious HTML, and it will return non-dangerous HTML that cannot execute any scripts. The library supports flexible configuration of what tags to allow and what to forbid. Here we are allowing only bold and italic text. What the purifier does is that it puts this HTML code in a virtual isolated DOM, iterates over everything, sanitizes the tree, and returns back a safe string. This sanitization can also be performed on the server side, but it is safer to do it on the client side, as then it uses the browser's built-in HTML parser and therefore is more reliable. This is because there is a risk that the parsing library used on the server side may fail to perfectly replicate the behavior of the parsing engine that is used by the particular user's browser, which may then result in a bypass enabling code execution. Anyhow, so that's about the HTML sanitization. With this we end the lecture. Thank you for watching.